Gravitational force. Simple near planet version. You'll get something more complicated that's truer to reality in chapter 13, but that lies in physics 1b. Alright, for now, simplified gravitation. The gravitational force, Fg, will just be equal in size, so magnitude, to the mass of the object times gravitational acceleration, where g is just 9.80 meters per second squared, or, if you prefer, 9.81 meters per second squared. If we're talking about it as a full vector, then it's the mass times gravitational acceleration as a vector, or m times g in the minus j hat direction, where g, as always, is the magnitude, 9.80 meters per second squared. This is only true near the surface of large, massive bodies. So basically, when you're someplace like the surface of the Earth. Now, here's the thing. G is only 9.80 meters per second squared if we're talking about the surface of the Earth. If you're on Mars, G is actually 3.71-ish meters per second squared. On the Moon, I think it's around 1.6-ish meters per second squared. It's about 1/6 of what it is on the Earth. So it depends on where you are, what it's going to be, and this is really only true within maybe 100 or so kilometers of the surface of the body. So here on Earth, it works really well when you're at the surface, around sea level. It works just as well when you're on Mount Everest, because Mount Everest is only 10 kilometers up. It's not that big a change. The Earth is about 6,370 kilometers in radius, so another 10 kilometers, more or less, isn't that much. If you're on the International Space Station, well, now it's a bit different. Your gravitational force there would be about 95% of what it is on the surface. It actually gets weaker as you go further away, but you have to get a long way away from the surface of the planet, a significant fraction of the radius, before it becomes seriously noticeable. Okay. Let's see, other things you might find interesting about it. It's a pairwise thing. So the Earth pulls down on you, and by third law, you pull up on the Earth. And of course that means it'll be the same size, but opposite direction. Yeah, so I have a mass around 90 kilograms, which means that it's about a 900 Newton force that pulls on me due to the Earth. So I'm being pulled down with 900 newtons of force, and that means I'm pulling up on the Earth with 900 newtons of force. But remember, second law is what determines acceleration, so I accelerate a lot. The Earth, on the other hand, accelerates almost not at all, because its mass is around 6 times 10 to the 24 kilograms, which I'm like 1 times 10 to the 2. 90 is almost 100. That's more than 22 orders of magnitude larger. That is outrageous. If I'm jumping up and down as hard as I can on the Earth trying to make it move, it's going to move. Its acceleration will allow it to move a lot less than the width of an atom from that motion. Like 6-7 orders of magnitude less than the width of a nucleus of an atom even. So yeah, it's a pretty cool force. It doesn't require contact. It acts through fields. It actually acts through the curvature of space-time, or so we think. Not really a field, but it's pretty neat. One of the 4 fundamental forces, and the only one that we deal with in this class by name. The other fundamental forces would be electromagnetic, strong nuclear, and weak nuclear, and we actually don't talk about them directly, although In the next video, we'll be talking about some things that are a direct consequence of the electromagnetic force. So yeah, that's about it. Gravitation is just going to be a force that acts downward. It has a size based on mg, and that's it. Oh, there is one other thing I should talk about. Weight. Not really same as Fg. It's not really the same thing as the gravitational force. So, weight with a T. Weight is really measuring the support force required to hold you up. So if you imagine getting inside an elevator and you've got a little bathroom scale, and then you come along and you stand on it and the elevator begins to accelerate upwards, right in the moment when it's accelerating, the scale will read higher. And it will read higher than the gravitational force acting on you. If acceleration is equal to 0, then the weight is equal to the gravitational force. But if you're undergoing acceleration, the support force, the weight that you effectively have, is not going to be the same as your gravitational force, the gravitational force acting upon you. It is going to be something larger or smaller depending on how you're moving. So in an elevator accelerating upwards, you will effectively weigh more. And in an elevator that's going downward, you will effectively weigh less. But the gravitational force is the same in both cases. So it's important to remember this difference these days to avoid the problems with using the term weightless, which seems to imply no gravitational force. NASA has gone to using the term microgravity, which also implies there's no gravitational force. We really need a better term than either microgravity or weightless for what happens in outer space, because when you are orbiting the Earth, the gravitational force acting upon you in low Earth orbit is basically the same thing as the gravitational force on the surface. So there's still a very significant force acting upon you until you get a long way away. Now we're done with gravitation, so we'll move on and talk about a couple other forces next.